Sometimes the very first time I start recording, it doesn't record, so I'm gonna restart it. So there'll be another video, but hopefully it'll make sure it works. Okay, so just make sure William's not on there yet. Still not on there. Okay. All right. Let's see. We talked about these two. Yeah, sampling can provide highly detailed information. It is possible to get enough information from sampling. All right. Of course, sampling costs less, so it allows us to repeatedly collect information. I don't know if you all are aware, we do, in the United States, we do a census every 10 years, but every year they take a sample and they correct that data, so you can get what they call census update values in the off years. Okay, and so those are created through sampling. And what's really neat is that they can, in the year they actually do the census, they can actually use that data to see how well their sampling techniques are holding up. And oftentimes, one of the advantages of sampling is that it can produce a high degree of accuracy. If you're not necessarily focused on going everywhere, you can look at things deeper and not so superficially. So you can take more points you can look at less overall points than looking at every single one, but look at those more deeply. All right, here's just a simple chart from the book that shows that obviously as the sample size increases, the amount of effort and cost and time goes up, and as you sample more, the level of inexactness and measurement goes down. So sometimes, and we'll talk about this in the second lecture today, or the second chapter 8, sometimes you're just interested in finding that, hey, if I want to only be wrong one time out of 100, how many samples do I need to take? You can answer that question assuming that you sample correctly. And so you can find out where you are on this X, this curve. That's actually a curve probably in real life, right? But those are just, in general, costs go up and the exactness of the measurement becomes better as sample size increases. Okay, so when we go about to estimate, that's the end goal, is the next chapter stuff. When we go about to estimate the values in a population, what we need to do is actually define that population. In order to come up with a real estimate of that population, we need to know what it is. And so, I mean, a really simple, maybe kind of silly example is that if we're trying to find out the average income in Mississippi, what's our population? It's Mississippi. We can't just go asking people in Lamar County or in Forest County what their incomes are. In other words, the population, I mean, the sample is a subset of the population, but it needs to be a real subset of that population. So we need to conceptually define that target population. And it's, when we're dealing with geography, it's really important that we define that area. Okay. What that area is. And it's very possible that if we're not careful there, that it won't be portable to other places. Obviously, if we defined it, we do the same thing. We collect a sample in Mississippi, we're not going to be able to apply that to the United States necessarily. All right. The next thing that we need to do is, based on this set of information, we need to designate a sample population and a sample area. So what we need to do is say, okay, these are the areas that we're going to these are the areas that we're going to sample from. We haven't yet defined the specific locations, but we've just defined the areas. Now, there also are some non-spatial sampling frames. Okay, so well, if I was trying to figure out who's going to win the next presidential election, and I only asked, either just Republicans or just Democrats who was going to win the election or who they were going to vote for, it's very likely that my that my estimate of who was going to win would be wrong, right? So it's not just about space. As geographers, we are concerned about space. So we do need to think, okay, well, I need to make sure that I'm getting a cross-section of the right group of people in my sample in order to be able to make the predictions that I want to make. So you need to define a non-spatial sampling frame. Okay. And then you need to identify that actual set of individuals or elements. They don't need to be individuals necessarily. Talking about maps, we could just be talking about specific units that constitute the sampled population, and then the same thing for the area. Okay. In other words, this is like about data acquisition. We need to get the data that we're going to take the sample from. And then finally, well, I guess not finally, but you got to choose a sample design, which is what we're going to spend some time next few slides in the lecture talking about. And then basically go out and do it. Lots of times you'll conduct a pre-test. So you'll take an even smaller sample of the data and see if it is performing the way that it should with the numbers. We'll get into that in the next chapter. Okay. When we, based on this, right, the amount of imprecision in the sample, okay, it's another way to say that is that we're going to, anytime we take a sample and make an estimate, we're going to have some imprecision, okay? Samples are never 100% accurate. The best way to ensure that they are close to the real value that we're trying to estimate in the population is to include an element of randomness. Randomness must be incorporated to represent population accordingly. Just see if it's William. No. All right. So any other method that's not purely random is going to introduce some systematic error. Okay. However, lots of these methods for sampling that we're going to talk about are easier than random. Sometimes random is hard, particularly with geography. Like if I do that map accuracy example, and I'm going to go out and actually find out if a particular area is what I say it is on the map. In other words, I flew a remote sensing mission, and I made a map, and I said that there's a wetland right here. Well, I need some way to verify that it is actually a wetland if I'm going to do an accuracy assessment, especially if I asked the computer to randomly come up with that dot. I have to choose it. Otherwise, if I say, nah, that's too hard, I can't figure out that one. I can only figure out this one. Well, what I'm doing is I'm probably inflating the accuracy that really is on that map, because I'm biasing it by places that are easy to get to, right? So the journal article that I was just talking about that we're trying to get published, the way that we fix this problem is our in the field accuracy started off with using drones to fly there, but even some places we couldn't get in our random sample, so we had to take a helicopter and fly there, which costs, I didn't actually pay for that or wasn't involved in that, but it costs a lot of money. So anyway, yes. So sometimes randomness is hard, and so there are ways to make some compromises, but the exercise will show. The exercise that you'll see will show you how it'll make a little bit of difference in terms of the estimates. Okay, so improper sampling design will make it so that your level of accuracy, your level of precision, both will go down. And most of these are related to these operational, logistic, and personal problems. The personnel problems. The ideal is random, but if you can't do random because of these other issues, then we'll talk about some other designs that work well. And sometimes you can find out if your data will be, if it's justified to use one of these. You can also make errors just, even if you go to the site and you say, well, this is really a wetland, but you write down in your notes, or somehow you have a button that you press the wrong button, you can still make errors. So one of the things about accuracy assessment or sampling is that the principles that we're going to talk about assume that your data was collected correctly. Okay, so we're not talking about mistakes. We're not accounting for mistakes. Of course, you could use these same principles to figure out how often mistakes occur and then try to model mistakes. But that's not what we're addressing today. All right, so we talked about this. Define your target area. The target area is a map area on a map. The target population is the complete set of individuals from which the information is to be collected. I guess another thing, like if we're talking about the income example, and we randomly selected a bunch of places, a bunch of addresses, and we asked them how much they earned. We asked everybody at those addresses that we randomly selected how much they earned. Well, what if we'd selected like a student that was being supported by their parents, but they still lived at a different physical address? You can see how that may or may not be something that we want to include in our set of a population. So that's an example of something that you have to think about. What's your population? Is your population people that are truly, establishing their own incomes in that situation? So sometimes what I'm trying to get at is sometimes these are easy things to think about. What's your total target area? What's your target population? But sometimes you need to refine that and make sure that when you sample, you throw out things that aren't actually part of your target population, if you're not trying to include those. Yeah.
So the best way to do that kind of example probably would it be like doing it by county? Like you would have you would focus on a county first, and then do do it according to that, and then just afterwards, I guess after you get every county done, you would do a weighted mean of that. Would that?
That's one way. That's actually called a stratified sample. And we'll talk about that in a second. But that's definitely one way to do it. Yeah, I guess what the thing that I was just talking about is if you're trying to report median household income, you would have to decide: does my population? Am I saying the median household income for what? Does that mean just every single household, whether or not they're a dependent, or is it median household income of independent households? Like, what am I actually trying to get at? And that's why I'm saying that your target population, you really need to think about what it is. Sometimes it's not always as simple as just saying, yeah, it's this, because there might be exceptions in your data. There might not. I mean, you might actually be just saying median household income regardless of. So in other words, for everybody that lives in a house, total of your income, what is that? That's the number I'm trying to get. But that's what you need to define as the target population. Then, if that's what you're trying to get. All right. Yeah. So here is where your sampling frame is like. I kind of picture it as an extent. Another way to say that, a frame is an extent. The sampling frame includes the sampled area and also the actual data values. So if you were to think about this, I do GIS work. I know not all of you necessarily do, but if you were to think about this and you had a data set that included, every home in the United States, or every home in the United States, and you wanted to get every home in Mississippi, that was your sampled area. But if you only wanted, people above a certain age, in other words, you were interested, like let's say you're interested in retirees, then your sample population should only include retirees. And so you would have to do two things in GIS. You'd have to, or that one of them wouldn't have to be done in GIS, but you could use a GIS tool to do it. So one thing is you'd have to get rid of everything outside of Mississippi, because your sample area is your population is Mississippi, and then you have to get rid of all of the people who aren't retired, and then you have all the households that are retired households. Okay, now you can start taking a sample. That's what this is saying, is that you need to sometimes, a lot of times, you have a data set. If you haven't been responsible for creating the data set, you'll need to create your sampling frame, and your sampling frame consists of filtering for just your population and just the area that you're interested in. Okay. It's just the sampling frame always includes filtering for just the population you're interested in. As geographers, we also need to remember the area. Okay, so we said that randomness is the ideal, and that's true. If we can't have pure randomness, and also, even though I said randomness is the ideal, if our sample gets small enough, that we do have the issue of sometimes excluding things that shouldn't be excluded. So sometimes it's necessary to make sure that we have a representative from each of the subsections. So that's another example of stratified there. So if they can't be random, we still want them to be probability based. In other words, we didn't choose them. Okay? And ideally, the ideal is random. In other words, every single thing that's in our sampling frame, in other words, every single element in the population, has an equal probability of being selected. That's the ideal, and that's the definition of randomness, right? So we're gonna take a sample, and that sample is going to be drawn, and every time we draw, we're gonna have equal opportunity to select everything in our sample frame. That's the ideal. However, there are some other ways to do probability samples, and those will approach every value has the opportunity to be equally selected, but you'll see that they each have elements of that. But sometimes, in the case of systematic, which is the first one we'll cover, once the first value has been chosen, everything else is selected in a systematic way rather than a random way. Okay? And we've got stratified, cluster, hybrid. These are almost in order of their desirability, I would say. Okay? We'll talk about each of them. Okay. And when we talk about systematic, it can be spatial or non-spatial. We talk about stratified, it can be spatial or non-spatial. Each of these can. We'll make some maps of the spatial examples of those. Okay, so this is where we go out and design the research instrument. Okay, it could be through direct observation, but in order to make less errors, less mistakes in the sampling, we need to establish protocols. We need to make sure that if it is a questionnaire type of a study, that if there are different people asking the questions each time, that they're asking them the same way, and that they're not introducing bias into how they ask the question. I mean, even things like, political questions, even the tone of your voice might change the response for some people, right? And so you want to hold as many of those things constant when you do that. Otherwise, it's not truly random. You're causing a bias, yeah, you got to think about the logistics, how you're going to visit all the locations or all the individual people, and that sort of thing. It's always best to conduct a pre-test, in other words, a trial run, to find out if there are any problems. So if you have several people asking questions, you could have each person ask a series of questions and see if there are any problems that are occurring, and that may result in adjusting the sample size, or it may be a good way to actually determine what the final overall sample size should be, and that is something that we'll talk about in the next chapter. So you collect your sample data, make sure you do it consistently as we've discussed. All right, so let's talk about these different types of probability sampling. So the first one is simple random sampling. If we're talking about that on a map, it would look kind of like what's on the bottom left. Simple random sampling means that all individuals in the sampling frame have an equal chance of being selected. So one way to do that is to have all individuals, like if it's a data table, all individuals in a data table, and then the number, just choose a bunch of random numbers, and those random numbers that are selected determine who or what elements are selected. Okay. So ideally, you'll get a bunch of points, and sometimes they'll be close together, and sometimes they'll be far apart. That's what randomness actually means. All right. So another probability-based method that works but it's not as ideal as random, is to have all individuals sequentially chosen by a fixed interval. And this works well a lot of times, and it will work as well as random will work, except in cases where there is a systematic nature to your data. And that can actually happen in spatial data. I should have had like a diagram of this, but let's just say that you have a terrain surface, and that terrain surface is gently like undulating up and down because of, like, depends on the scale, but maybe because of wind or water or faulting patterns on the landscape. The elevation goes up and back down, and there's like valleys and peaks, but that exists somewhere out west. So if I was going to try to sample the population, if I was going to try to sample the temperature values, if I came up with a systematic sample every 10 miles, and I happened to always be at higher elevations, the temperature would be higher. See what I'm saying? And so that could be a problem. So choosing individuals sequentially on a fixed interval is okay if there's no way to assume that your data itself doesn't have a sequential pattern. One way you could do that is to line up all your data in the same order that you'd be selecting systematically, and just do a time series graph of it. And if it's like going like this, then you can't choose a systematic sampling scheme. Right? Of course, it would, like if I had the average temperature every month. I mean, just this is another example of why, of course, it wouldn't work, right? So I have an average temperature every month, and I wanted to find out the average yearly temperature, and I just selected every 12 values. I would get the average temperature for just that month. It wouldn't be a representative of the average temperature that whole time. So that wouldn't work. Okay, so next one, stratified sampling. Stratified sampling is, like Addison pointed out here, it's dividing the population into subgroups and then sampling those subgroups. And one way to do that is proportional. Like if you know, for example, that, well, like in the presidential example, if I know in a particular area that there are 60% of the people are registered Democrats and 40% of the people are registered Republicans, I can proportionally stratify that sample and include let's say my sample was just 10 people. I can make sure that I'm going to get 4 Democrats, 6 Republicans in that scenario. That would be an example of a stratified sample. Now, disproportional means that the population ratios aren't maintained in the subgroups. Now, this is a little bit more problematic. If you do proportional, in some cases, if there's no reason to assume that you had bias in how you picked the individuals in the subgroups, you can still use the same techniques that we'll talk about for simple random sampling. However, if it's disproportional, or you have no idea what the actual population ratio is, you have to assume it's disproportional, and then you have to do different. There's different techniques to estimate the overall population. Okay, so in most cases, that's what happens. Is that if you do disproportionately sample, it's just that you wanted to ensure that you got the minimum number of samples, which usually we say is about 30, and we'll talk about why that is later. But you wanted to make sure that you get at least 30 from each group. Then if you have 30 from every group, you probably got a disproportionate sample if you want to make any estimate of the overall value. And so you have. Yeah.
Would Addison County example fit disproportional since the populations in different counties would be different?
Well, it could fit either one. So proportional would mean that we would make sure that we, in other words, if Lamar County has 2% of Mississippi's population, then 2% of our points would come, our sample points would come from Lamar County. That would be proportional. So if we were going to collect 100 points, 2 of them would have to come from Lamar County, right? That would be proportional. Disproportional would just mean I just want to make sure I get 5 points in every county. And so then I get 5 points in every county, and I have to do some additional math. It's basically it's almost the exact same math in terms of doing the weighted mean, but now you have to make sure that you do it. You have to do it on the estimation of the actual mean. Does that make sense? And we haven't gotten to the math, but it is about the same as that. So yes, either one is fine. I mean, either one's fine. Either one works, but this one requires a little bit of additional work to do on it. But the advantage to doing this is, like I said, typically you want 30 samples. And so my example was a little bit off, but let's say we wanted to get 1,000 samples of all of Mississippi. One way to do that is to randomly sample everybody in Mississippi. But then we don't have the information we need to go into every county and make a judgment about that county. Because in some counties, we may have only gotten 2 or 3 observations, right? Like if we did a truly random sample, even if we sampled 1,000, there's going to be some counties that got under that 30 threshold. How many counties are there? There's 82 counties. What's 82 times 30? Just make sure I'm scaling my numbers right here. 82 times 30 is 2,460. Okay, so one more modification. Let's just say that I wanted to sample 2,500 in all of Mississippi. Well, if I did that, there's going to be the average number of points in every county, if it's truly random, is going to be 30. But it may not be that I get 30 in every county. I may only get 10 in some counties and 40 in others, right? And so what I'm trying to say here is that the advantage to doing a disproportionate sample in this case is that now I have enough samples in every county to do some of the estimation that we'll talk about in the next chapter. And so I can come up with an overall value for all of Mississippi, but I can also come up with an estimated mean, like if we're talking about income, I can come up with the mean income for every county, and I can come up with a mean income overall. It's just that I need to do the disproportional math rather than the proportional math if I do that. So that's why. And then doing the accuracy assessment example that I talked about before, it would be very, very similar. That if I wanted to come up with, if I wanted to say, okay, well, how well did I map the wetlands, and how well did I map the forests, and how well did I map the urban areas? If I just did a random sample, I may only come up with 5 wetland areas because wetland isn't very common in my map. So I may only have taken 5 samples in the wetland. 5 is not a good enough number to know how well the map accuracy of wetlands is. I need at least like 30 or so. And so I would allocate my resources to collecting as much in each, and that would be disproportional. Again, the ideal is to randomly sample your population so that you do, like let's say I came up with a random sample and I decided with the income of Mississippi example, the ideal is that I come up with a random sample and I do have 30 points in each, but that might take me actually collecting 7,000 or 8,000 data points in order to make sure I got 30 in each, doing purely random. Okay. So I might not have the resources to do that. So that's why I would shift gears and do a stratified sampling technique and make sure I got enough in each category. But if I did, then I may end up being disproportional, and then I'd have to do the other math that we're going to talk about in Chapter 8. Yeah, I mean, or another way to do that, to come up with another way to come up with that compromise is to find the county with the smallest population and say, okay, well, I know I need 30 of this. I know I need 30 in this county, and then I scale that up and find out, okay, if I need 30 in this county has twice as much. That means I'm going to need to do 60 in this county. And then I could figure out what the minimum number was, and it might be better to do a proportional in that case. And then if you do a proportional, you can pretend that it was random, pretty much. Okay. But if it's disproportional, you have to do the other stuff. All right. Now these other ones that we're going to talk about, cluster sampling and hybrid sampling, since they're getting further away from random, we're not really going to talk about how to estimate the values in these. So if you did a cluster sample or well, actually, never mind what I said about hybrid. Hybrid's different. So we're not going to talk about cluster sampling when we get to Chapter 8. But if you do a cluster sample and you can demonstrate that your cluster is still pretty close to what you would have gotten with a random sample, then just use the random sample values. Okay? So a cluster sample is where you divide it into areas, and then you sample things that are nearby or similar. Okay, so if we're doing it spatially, it would look like this. So that's how you do that. And again, just like systematic, you bring in the opportunity for bias when you do this. And so what would be great is to since some of these values could be calculated again and again, you could hold out some of the values and see if the numbers were changing that much to kind of demonstrate that it was close to random. But in any case, if there's any degree of bias, you're not going to be able to make a reliable estimate of the overall population. We're always assuming that's random. And the only thing that we can really correct for is the stratified disproportionate. Using the techniques we're talking about today, we can't really correct for any of these other things. So if it's systematic and you're introducing bias, then that's a problem. Okay, there's not a solution for it. And if it's clustering and you're introducing bias, then there's not a solution. Hey, an example of a graph that might be good to look and see if you're introducing bias with your cluster sample is to make a box plot of all of these data sets, then all of these, and all of these. So a box plot of every cluster. And if the clusters themselves don't look like they're way different than each other, then you're probably good to go. Okay, that's what you do, is you hope that you're good to go. All right, a hybrid sample. None of these things that we talked about are mutually exclusive. So you could mix and match these, and in fact, you could do a random sample, and then within your random sample, you could stratify it, or you could stratify it and do it randomly. So in other words, if if we took, if we did going back to the counties example, if we made sure we had 30 in every county, we could still randomly select from those 30 in that county, or we could do it systematically. We could select every third observation in each county, something like that. So we could also do random clusters. In other words, we could say, okay, well, we're gonna check these 5 locations, but at those 5 locations, we're gonna go 10 paces to the north, 10 paces to the south, 10 paces to the east, and 10 paces to the west at each of those 5 locations, and find out what the value is at that location. That'd have to be that'd be something like water quality. Okay. Now, if you did it like that, you'd still want to see if all of your cluster values were very similar. You can't use those as individual operations. One thing you could do with cluster samples is you could use clusters to check for inconsistent data collection. In other words, if you had one data point in your cluster that was way off, you could assume, oh, somebody just messed up when the instrument was off, or somebody messed up when they did that value. So clusters can be used for other reasons, but you'd have to come up with like an average value to do that. All right. So how do we sample? There are tools in ArcGIS for doing all these sorts of things that we're going to talk about now, but I'm not really going to execute them in class. But we'll talk about how to do that, and we'll go into a little bit more detail for point sampling. Okay. So in any case, if we're just talking about features, you need to make sure that every feature in your database, whether it's a point line or a polygon, a point area or a point, polygon, or line, or we could say an area, whether it's any one of these, we need to make sure that every single thing in the database is a distinct element. In other words, if we're trying to, like if these lines represented roads, we're trying to come up with an estimate of how many potholes exist in our town, and we're going to do a random sample because we don't want to check every single road. We're just kind of trying to come up with an estimate of how many total potholes there are. When we random sample the lines, we need to make sure that the lines are all discrete elements, and that they're not like if one line is all of Hardy Street and another line is just like a little piece, that's introducing a bias into that area. Into that sample. It's basically like stratifying our data. So we may need to use the stratified samples math in the second chapter. Okay. In chapter 8 is when we'll talk about that the next lecture. Okay, so one way ArcGIS does allow you to do both of these. So you can if you have a map and you're trying to come up with sample locations, you can just give it an extent and it'll come up with a random point sampling scheme, and then you can just go visit those locations. You can also systematically sample an area. There's a tool called Generate Tessellations. We used it already, and it'll allow you to create a evenly spaced set of points. All right, so here are a few different types of sampling schemes that are used in geographic problems. This is the ideal, the simple random point sample. Okay, this is an example of it. A systematic point sample, and then this is a proportional stratified point sample. In other words, they're not an equal number of points. There are more points in this polygon because it is larger than there are on this polygon. Okay. Now, it could be proportional in two different ways. Like if we're just talking about land units, you'd want it to be proportional to area. But if we're talking about people, we'd want it to be proportional to the number of people in each of these polygons. Okay. Here's a disproportionate stratified point sample where we have roughly equal number of points in each. Okay. The reason why this one looks more crowded is because it's a smaller polygon, and so those points, they look more crowded. Okay. And then these are clusters. Okay. We might randomly select which cells we're going to sample in, and then randomly select inside of those. Right. And ideally, we get close to random if we did random. This is going to cost us less to collect this than it would to collect the same number of points in an area. Whether it's in time or actual dollars to pay people to go there, this is going to cost less. The problem is if there was some sort of systematic, like in other words, if in this area, if this area was way different than the rest of that area, then we just made a mistake. But if we can assume that everything's kind of uniform in that study area, then we probably didn't make a mistake. But we'll never know because we didn't collect any data over that. So that's what I was saying. If you're going to use a cluster technique, sometimes it's good to first do a stratified technique, find out if there's any biases in your data. In other words, does the data seem pretty uniform? Okay, do I have values that are or is there something systematic in my data? Then I could investigate another area more. These are just slides from a different book. Same technique. There's another example of a disproportionate, stratified, systematic, aligned point sample. So there's all sorts of different. That's what a hybrid means, that we use two different techniques. Here's a stratified, systematic, unaligned point sample. In other words, we make sure that we select at least one point in each area, but we randomly select the actual point inside of that area. Let's make sure that we get coverage, so there won't be any systematic bias that's larger than these squares in our data, or smaller than those squares. All right, this is just a bunch of diagrams of different point samplings. So this would be clustered but then systematic, disproportionate, stratified cluster point sample. Okay. All right, but the ideal is that every value has an equal chance of getting selected. So random. All right, 211. Yeah, so why don't we take today we'll take like a 9-minute break, and so we'll come back at 2:30, or sorry, 2:20, and then we'll continue, because I do want to finish by 3:30, 3:40, like I said I would. So I'm gonna stop the recording there.